So for this session, we'll be having some problems that are related to lecture 1.4, differentiability, differentials, and local linear approximations. So I assume that you've watched the related lecture videos. So we'll just recall the concepts whenever we need them. Okay. So let us start with our first problem here. Let f of xy be this function 8x squared y cubed minus ln of 2e to the xy. The first problem is we want to find the equation of the tangent plane at this particular point. And then the second problem here is we need to use the result in here, in number 1, to approximate this value here. So let's just quickly recall how we are going to write the equation of the tangent plane. It's this way. So z equals f of AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. Okay? Assuming that your first partial derivatives exist. Okay? Assuming that the first partial derivatives exist. So, in this case, we want the tangent plane at the point 3, 1/2. So, let's start with f sub x at any point x, y. So, we are getting the derivatives with respect to x. So, we will treat y as constant. So, in this case, we will have here, with respect to x, we'll have here 16xy cubed minus, we have this ln. We have this ln of 2 times e to the xy. So we have the x there. So we'll just get the derivative of this. We will have 1 over 2 e to the xy. And then by chain rule, we need to get the derivative of what's inside that ln function. But since we're differentiating with respect to x, the y here is treated as constant. So we will just have 2y. And then we have the derivative of x, or e to the x with respect to x. It's also e to the x. Which means that in here, if we try to simplify, this is just 16xy cubed minus 1. So this is f sub x. And then if we evaluate this f sub x at 3, 1/2, we will have 16 times 3 times 1/2 cubed minus 1. This will be equal to what? So 1/2 cubed, that's 1 over 8. 16 over 8, that's 2. So we will have here 6 minus 1, and this is equal to 5. Next, let us get f sub y, x, y. So this time, we are differentiating with respect to y. We treat x as constant. So if we get the derivative of this with respect to y, we will then have 24 x squared y squared. And then for this guy, since the argument here contains that variable y, and we are differentiating with respect to y, we'll get the derivative of this, and then we treat to e to the x as constant. So we will have minus 1 over 2 e to the x y times, by chain rule, we multiply by 2e to the x. So if we simplify this, we will have 24x squared y squared minus 1 over y. Therefore, if we evaluate this at 3 comma 1 half, we will have 24 times 3 squared times 1 over 2 squared. And then minus 1 over 1 over 2. So this will be 1 half squared, that's 1/4. And then you will have 24 over 4, that's 6. Then 6 times 3 squared, or 6 times 9, that's equal to 54. And then 1 over 1 half, that's just 2. So this is equal to 52. Now we also need f of AB. So f of 3 comma 1 half. This will be 8 times 3 squared times 1 half cube minus ln of 2 e to the power 3. Okay, e to the power 3 times 1 half times 1 half. So if we simplify this guy here, it's 1 over 8, so it will cancel this. So we'll just have 9 on this part. On this part, we will have 2 times 1 half, that's just 1. So we have here ln of e cubed, and that's just 3. So this is equal to 6. Therefore, the tangent plane at 3 comma 1 half is given by the following equation. So we will have z, this is equal to 6. And then f sub x, that's 5. So we have here 5 times x minus a. So x minus 3 plus we have f sub y, that's 52. And then x or y minus 1 half. So this is the equation of the tangent plane. Okay. Now, did I miss a computation here? So anyway, we want, for number 2, we want to use the result that we have obtained here. It's this guy here to approximate this value. Okay. So how do we approximate this value? So we use local linear approximation. And the local linear approximation, it's almost the same as the value at the tangent plane. Correct? So this guy here is actually, with our notation, using our notation, this is our L at the point x comma y. Okay? And of course, if we have to put the subscript, we need the subscript 3 comma 1 half. Okay? Just to emphasize that the local linear approximation, or this equation here, is the one that is very close to 3 comma 1 half. Let me put that one. Okay, so let us put that, L sub 3 comma 1/2 of x comma y. So meaning this guy here can approximate the value of f if the point x comma y is taken to be very, very close to 3 comma 1/2. Okay? So, let me label this guy here, this expression here, as maybe let's put this as f star. Okay? So that f star, okay, in fact, it's f of 3.01, comma 0.49. So let us put that one instead of f star. This guy here, it's the evaluation of the function at 3.01, comma 0.49. So try to observe. This is 3.01, that corresponds to x here. This guy here, it's 3.01, so that corresponds to the x there. 0.49, that corresponds to the y. You have this 0.98, but that's just twice of this guy here. So clearly, this guy here, it's the evaluation at the point 3.01, comma 0.49. So what does this mean? This guy here, f, so we are now doing number 2. So f of 3.01, comma 0.49. This can be approximated by L with subscript 3 comma 1/2 at that same point. Correct? We have here 3.01 comma 0.49. So using this guy here, we will have 6 plus 5 times, you have 3.01 minus 3, plus you have here 52 times 0.49 minus 1/2. Let me put that as 0.5. And therefore, this is just 6 plus 5 times 0.01. And then 0.49 minus 0.5, that's negative 0.01. So we will have here minus 52 times 0.01. Okay? So simplifying this, what will we get? We will have here 6 plus 5 times 0.1, that's just 0.05. And then here, minus, how do we subtract, how do we multiply this? If we multiply this, we have 0.52. Correct? Did I multiply it correctly? So 1, 2, and therefore we move this by 2 decimal places. So 0.52, which means this is just, what is this? 6.05 minus 0.52, we will get 5.53. Okay, 5.53. So it says that the value of this guy here will be close to 5.53. Okay? Let's check the value using some calculator. So I am getting, or I'm going to use Wolfram alpha. Okay. So let's see. Let me share that Wolfram alpha window. So we want to find the value 8 times 3.01 quantity squared times 0.49 quantity cube minus ln of 0.98 e raised to 3.01. So look at that. The value, it's 5.53750. So it's really close enough. 5.53750, etc. And what we obtained is 5.53. Okay? So, questions? Okay? Let's look at our next problem. Find the local linear approximation of f of xy given by this expression here, square root of x plus sinh 3y at the point 1, 0. And then use it to approximate f of 0.98, 0.01. So very much similar to the previous problem. So first, let us find the local linear approximation. And again, we just need the tangent plane. Okay, the expression for the tangent plane, okay, that will be our local linear approximation. So we need f sub x of xy. So partial derivative of f with respect to x. So this is square root of x plus sinh of 3y. Partial derivative with respect to x, we will have 1 over 2 square root of x plus sinh 3y. Okay? And then by chain rule, this is just multiplied to 1. The derivative of x with respect to x is 1. The derivative of sinh 3y with respect to x, that's equal to 0 since y is treated as constant. And now, from here, we evaluate. So f sub x, we evaluate this as at 1, 0. We will have 1 over 2 square root of 1 plus sinh 0. Sinh 0, that is also 0. Therefore, this is just 1 over 2. So this is f sub x. F sub y, x comma y, we will have here. So we are now differentiating with respect to y. Same as in before. We have 1 over 2 square root of x plus sinh of 3y. And then by chain rule, we multiply by the derivative of x plus sinh 3y with respect to y. So derivative of x, that's 0. Derivative of sinh 3y, that will be cos 3y times 3. So let me just write it here. 3 cos 3y. Therefore, if we evaluate this at the point 1, 0, we will have 3 cos, so 3 cos of 0, and cos 0, that's just 1. And then we have here 2 square root of 1 plus sinh 0. So this is simply 3 over 2. And then we also need f of 3, oops, f of 1 comma 0. And this guy here, it's just 1 plus sinh 0. We take the square root of that. This is just equal to 1. Therefore, we have here the local linear approximation at the point 1 comma 0. This is given by f of 1 comma 0. So that's 1 plus f sub x evaluated at 1 comma 0. This is 1 half multiplied to x minus 1 plus f sub y evaluated at 1 comma 0. That's 3 halves. And then you have y minus 0. So this is the local linear approximation at that point 1 comma 0. And then for the follow-up question, we want to use this equation here in order to approximate the value of f of 0.98, 0.01. So f of 0.98, 0.01, this is approximately equal to L sub 1, 0 at 0.98, 0.01. But this guy here will just have 1 plus 1 half times 0.98 minus 1 plus 3 halves times 0.01. So in here, this is equal to 1 plus, we have 1 half times 0.02, actually negative. So this will become minus. And then plus, so let's put everything in decimal. So I'll change 1 half to 0.5. And then 3 halves, that's just 1.5 multiplied to 0.01. So in this case, we will have 1 minus 0.01. Please check that arithmetic there. And then in here, we will have plus 0.015. Okay? And therefore, what will we get? 1 minus 0.01, that's 0.99. And then you add 0.015. So this will be equal to 1.005. So if all the arithmetic computations here are correct, then that will be the final answer. But again, let's just check using our Wolfram alpha in here. So let us have that. Let me share. So in here, we have now square root of, we have 0.98 minus sinh, or it's plus sinh. So plus sinh, I hope Wolfram alpha will recognize sinh. So 3 times 0.01, close parenthesis. Yep, so we got here 1.00499. Okay, and what we got was 1.005. So really close to what we obtained here on this part here. Okay? So questions? Okay. Next problem here. Use differentials to estimate the amount of tin in a closed tin can with radius 4 cm and height 12 cm if the tin is 0.02 centimeters thick. So based on the data, let us assume that the tin can is actually a right circular cylinder. So let's just visualize that. So we have this, say this tin can here, and then we have here the radius R, and then the height here, this is our H, okay? And therefore, we'll have the volume of this right circular cylinder. So in terms of R and H, this is equal to pi R squared H, okay? Now, let us look at the shape of this, or maybe suppose this is our tin can viewed in front of the can. So according to our data, we have here height equals 12 cm. And then the radius, it's from this and this. This is equal to 4 cm. Okay? And then according to this, the thickness of the tin is 0.02 cm. So let us just put some thickness on this part. Okay? So that's the thickness of our tin. That includes, of course, the boundaries on the outer part of the can. And then we want to use differentials to estimate the amount of tin of this tin can here. So, of course, the idea will be we will subtract the volume of the tin can as if it was solid minus the amount of whatever inside the tin can, the volume of that whatever inside the tin can. And of course, whatever inside the tin can, suppose it's completely filled up. Say we have this part here, okay? It follows the shape of your tin can, okay? Then if we only look at that circular cylinder inside the tin can, then this here, the height here will have measurements 11.96 because this guy here, it's 0.02 centimeters, 0.02 centimeters. Also on this guy, this part here, it's 0.02 centimeter. Therefore, here we'll just have 11.96. And of course, for the radius, so from the center going to this part here, okay? Going to this part here, the radius will just be 3.98. Because of course, the thickness on this part is 0.02. So again, 11.96 for this because we have 0.02 here, 0.02 here. So total of 0.04. And then in here, we just have 0.02. So 0.02. We'll just subtract that. Okay. Now, for the differentials, recall that the differential dv, this will be equal to partial of b with respect to r dr, and then plus partial of b with respect to h dh. Okay? Now, we want to calculate v of v of 4, 12 minus v of 3.98, 11.96. So this is your delta v. And this is approximately equal to the dv. Okay? And then in here, our delta r, this will be, we assume that this is equal to dr, and our delta h, this is our dh. Okay? Or let's write it on the other way around. So the dr, that's your delta r, and the dh, that's your delta h. Now, the change in the radius, it's just 0.02, while the change in height, it's 0.04. Okay? Now, let's find dv or partial b with respect to r, and then we will evaluate this at the point 4, 12, or at radius equals 4 and height equals 12. But look, partial b with respect to r, it's just 2 pi r times h. And then at r equals 4, h equals 12, partial v with respect to r will be equal to 2 times pi times r, which is 4, times h, this is equal to 12. And therefore, what is this? We have 96. Okay? This is equal to 96 pi. For the other one, we have dv over dh, or partial b over partial h. This is simply 2 pi, or this is simply pi r squared. Okay? And at r equals 4, h equals 12, we will have partial b over partial h. This is equal to pi r squared. So r equals 4 squared. So this is equal to 16 pi. Okay? Therefore, delta v, this is the amount of ping. Okay? This is approximately equal to the dv. And this is now, the dv is now equal to partial v over partial r. So that's 96 pi times dr, which is our delta r, that's 0.02. And then plus partial v with respect to h, that's 16 pi times our dh, which is 0.04. Okay? So if we calculate this, this is equal to, let's calculate this. So we have 32 plus 96 times 0.02. So let's see. So this is around 8.0424772. So this is just an approximate value. Okay. Or let's see. To two decimal places, we have here 8.04. And then this is change in volume, so the unit here is centimeters cube. Okay. So for our last example here, we have let f of x comma y equals x tangent inverse of y plus y tangent inverse of x. We want to determine if f is differentiable at the origin. So you can do your definition, but that would be hard. So we will use some theorem. The theorem that we're going to use is we look at the first partial derivatives of f and then check if they are continuous at the origin. If so, then the function is differentiable. So I hope you remember that theorem. So for this, we have f sub x, x comma y. So derivative with respect to x, we will have here tangent inverse of y. That's for the first guy here. For the second guy here, derivative with respect to x, this will be y. So we have plus y over 1 plus x squared. And then clearly this guy here, this is a continuous function. Both this guy and this guy, they are both continuous, so their sum must be continuous. So this implies here f sub x is continuous at the origin, since in fact it is continuous everywhere. And then you have f sub y, x comma y, this time with respect to y. So here we will have x over 1 plus y squared for this part. And then for this part, it's just tangent inverse of x. And again, clearly here, this is continuous everywhere, which means that f sub y is continuous at the origin. And by the theorem, this implies that f is differentiable at the origin. In fact, it's differentiable everywhere.